Okay, so I'll start. May I request the uh, people joining to kindly mute their mic because in case there's a disturbance, you can always unmute and ask. Thank you very much. So, okay, so good evening. We'll get started. So, I welcome the viewers to this problem solving and live interaction session for the subject Strength of Materials offered by Professor K. Ramesh on the Swayam portal. So my name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Today we'll be discussing the contents of week 5. So before we begin, are there any questions? Okay, so I'll get started then. So let us look at the first question. It says there is an assertion that the concept of stress and strain can be applied to isotropic materials only. And the reason given is the basic definition of stress and strain changes with the material chosen. So what we saw in the previous discussions was that we have displacements and we want to relate them to forces but we don't do it directly. Instead, from the displacements, we calculate the strains, and from the strains, we go back and forth between stress and strain using something called the constitutive relations, and we can integrate the stresses back to get the forces. Now it turns out that for different materials, we will have different constitutive relations on how they are, how the stresses and strains are related. But essentially, the definition of how stress and what stress and strain is doesn't change with the material. So the basic definition of stress and strain doesn't change. However, the constitutive relation will definitely have a bearing on how these two are related. For example, for isotropic materials, as we will see, uh, for a normal uniaxial tension case, we saw that it is the very basic Hooke's law, which is sigma is E epsilon. Now, as we go into more and more generalizations, this relation will keep getting a bit complex. However, it can still be related to stress and strain. So this is actually uh, it depends on the material. The constitutive relation depends on the material, but as such, the route which we take, the stress and strain route relating, that doesn't change with material chosen. So this can be applied to any material, not isotropic material alone, with the caveat being the constitutive relation would change. So both these statements are not correct actually. And in case you have any questions, you please feel free to stop me midway and you can unmute and ask. All right. So let us look at the next question. Dhruv decided to measure the strain on a composite cantilever specimen. So there is some information given. So we have a cantilever specimen. Let me draw the cantilever specimen like that. Let this be the side section and let this be the top view. So the cantilever is maybe fixed like that. So he decided to measure the strain on a composite specimen by made by fixing the gauge near the fixed end at the top of the cantilever. So what he did at the top, he has pasted a strain gauge essentially. I'll go into what that is. We'll come to that in a minute. So he has pasted and this is a composite material. At the top of the cantilever, his objective is to accurately measure the tensile strain while also accounting for potential heating losses. So what which of these strain gauge resistances would be the most optimal for precise measurement is what is asked. So let us try to understand a bit about strain gauges. Uh, these are essentially these are for point-to-point measurement of strains, and this can measure only axial strain. One single strain gauge can measure the strain along its own axis. So howsoever we orient it along that axis, it will give us the strain at that very point. And this works on the principle of a Wheatstone bridge, which we have seen in our high school. So basically for a Wheatstone bridge, which is excited by some voltage. So there are resistors like this. So I have resistors like this, and I have the output that is being seen here. So this is the input. Let us say I excited by a voltage V, and this is the output. So initially when I balance the bridge, so there will be no current flowing. So I won't be uh, actually measuring any output current, output voltage. Now what happens is, for example, if I were to replace this resistor by a strain gauge, that is if I take the same example, if I instead in these three resistors remain the same. Now this fourth resistor, what I do, I tap from my strain gauge and I connect it like this. So what I have done is, now when I'll remove this arm and just briefly explaining it. So when I connect it like this, now the moment I load this, there will be a change in the length of the strain gauge. Is essentially, it is a foil made of a wire. So when it is faithfully pasted onto the specimen and I load the specimen, there will be a change in its length. The change in its length and its change in its cross-section area will actually contribute to a change in its resistance. So an initially balanced bridge which was measuring no voltage will start measuring some voltage by virtue of this change in its resistance, which I can calibrate in order for me to get directly read out strains. There are procedures to do that. So this is the basic principle of strain gauge. So when I load this, there is a change in the resistance which disturbs the initial balance of this Wheatstone bridge. And I will be actually measuring some output voltage there, which I can calibrate to the quantity strain. So the more I load, more will be the disturbance, more will be my output voltage, and more will be the strain that I read. This is the basic principle behind this. Now it turns out that if I don't load, but instead if I heat, if I conduct this experiment, if Dhruv conducted this experiment in a room which suddenly underwent some temperature change, so naturally there will be thermal strains. So the foil, that will also increase in its length. Once it increases in its length, naturally it will lead to a change in the resistance, which will get captured by my output voltage. But my purpose of using the strain gauge is to confine its applicability to measuring mechanical strains, not spurious strains which are caused by environmental changes. So it becomes very essential that we account for heating losses due to heating of the strain gauge because of some environmental reasons. So in such cases, we see that the loss is generally given by I squared R. So what happens if I shoot up my resistance a lot, keeping the voltage same? If I shoot my resistance up, then the current flowing in the conductor will reduce. So, which means that if I actually have a higher resistance, it will be more robust in the case of a temperature, in the case of fluctuations with respect to temperature changes. Now, this question qualifies that we have a composite material. Composites are, as it is discussed in the lecture also, these are materials where we align the fibers in order to suit some specific purpose. And these are very poor conductors of heat. So there will be no dissipation of the heat, which means the strain gauge would be experiencing the heat with nowhere to dissipate it, which will again disturb our readings. So in such cases, it is better we go with a higher resistance strain gauge, so that the losses are confined and it is more robust for our mechanical measurements. So in this light, ideally, whatever, if there were other resistances given which were higher, we should essentially be choosing the highest of them all to make precise measurements of our mechanical strains. Are there any questions? Okay, so if you get any question, you please do ask. This is, yes, yes, please.
Is there any cutoff beyond which you would have, it would not affect your sensitivity?
No, essentially, this resistance is not the only thing that plays a role in this, because initially we will have to balance out the bridge also. The most common application we find is 120 and 350 ohms. But for special applications, because the Wheatstone bridge needs to be initially balanced, and we will see later that in order to maximize the efficiency of the Wheatstone bridge or maximize the signal of the Wheatstone bridge, it is preferable that all the resistors are of equal resistances. So considering that also, we need to decide on the strain gauge. It is not just that we can blindly go up and take a higher resistor. So considering all the possibilities, we'll have to take a call. I'm not sure if I answered your
Okay.
question. If I have not, you please post your follow-up question.
Sure.
Yeah,
No. I mean, I think it's all right. I was just trying to understand. So I appreciate that it might be a
yeah.
complicated thing. So I was just trying to understand from a, you mentioned about noise
Yes.
within the
So
signal.
yeah,
So
essentially that would appear that okay, if I were to go for a higher resistance, why not? Technically speaking, then there is no limit to where I can go. Yeah,
exactly. So
yeah,
where would the curve sort of
yeah.
flatten out
Those
what I
curves,
was
if
trying
you
to
see, in
understand.
order to maximize the efficiency, where the ratio of the resistors where it reaches one, where it is maintained at one, that is where it gives the maximum output. Beyond that, also your efficiency output drops. So there,
Okay.
in that
Understood.
case, I have a constraint that I have to maintain all these four as same resistances. So whatever is available and whatever is the material, based on that, we will have to take a call. Yeah. All right.
Okay. Thank you.
Okay. So this is the basic principle behind strain gauges. Granted, I did not draw a very neat figure, but I suppose you get the gist of how it is used and what it entails. All right. So let us look at this question. Which of these is best suited technique for whole field measurement of strains? So let us look at what this whole field is. Let us say that I have a body which is subjected to some tractions, etc., and some body forces, whatever. Now, if that is as we saw, if I place it in a coordinate system, for example, and then we will be given a displacement field, so to speak. So at every point when I plug in xyz, it will give me a displacement vector. From that I will get to strains and so on. Now, if I am able to measure the displacements throughout the body at one, using some experimental technique at once, that is, I get how the strains are varying or the displacements are varying across the strains, displacements, or any kinetic quantity for that matter. If I'm able to see it at once for the whole field meaning the entire domain of my interest, that is what is called a whole field measurement. Otherwise, I have to select point. Now we saw that in this example, Dhruv would be able to get the strain only at this point by this apparatus what he has made, because he has fixed the strain gauge here, and he will be able to get strains only along that direction at that very point. So at any other point when he wants to go, he would have to pace the strain gauge again, calibrate it, and so on. So that is what makes it a point by point technique. Is it necessary that point by point technique should not be adopted? No. It all depends on what our availability is and what our needs are. For example, if I were to design some component where I know for a fact that my area where the stresses are going to peak is known already, then I would naturally confine my attention to that point alone and try to make precise measurements. Otherwise, in order to get an overall global picture of how the behavior is, I might require some whole field measurement. So it is not that one is superior to the other. It is dependent on what our problem is. What is the output that we want out of our problem? So it is not that strain gauge being a point by point technique is inferior in any way. It is all dependent on the application that we are looking at. With that light, if you were to revisit this question, which of these is best suited technique for whole field measurements of strains? So strain gauge, we clearly saw it is not whole field because it is point by point. Photoelasticity, photoelasticity as we saw is essentially, this has two variants. One is reflection photoelasticity and transmission photoelasticity. The other is also based on the one. Okay, let me give a slight introduction to that then. I think that would be better. So, photoelasticity, as we saw in the previous session, very briefly, we saw that it works on the principle of stress induced birefringence. So, I have a material, let us say, it is, if it is a photoelastic material, what will happen is when I stress this, it will be transparent. When I stress this, at each and every point, it will develop two refractive indices. Because of that, some patterns will get formed in the plane. When I put it in one correct optics, I take a light source, I put it here, and then I view it from here. When I load this, I'll be able to see some patterns. Those patterns essentially represent contours of constant principal stress difference. We saw what principal stresses are, the sigma 1, sigma 2, and sigma 3. For the sake of this discussion, I'm confining to the attention of the plane of the paper. So if I were to take only these two, then whatever pattern I get, let us say that I get patterns like that. Some of the patterns are also shown in the lecture, so you can just see those are colorful patterns. So what this pattern essentially represents is sigma 1 minus sigma 2 equal to some constant k, some number which has some information about the material and so on. The other one, the other contour will be sigma 1 minus sigma 2 is equal to k1, some other number. So this is essentially giving us information of how the principal stress difference is varying across the field, throughout the field. Now this, as we saw, that there will be a light source and we will have an eye, we will be seeing it from the other side, and we will let light pass through that model. We will allow the transmission of light through the specimen. In that case, this variant is called transmission photoelasticity. Naturally, this will be applicable for materials which can let light pass, which means they have to be transparent. So essentially, materials like epoxy, polycarbonate, perspex, glass, all these are photoelastic materials which can allow light to pass. Although glass is a very poor responding material in terms of photoelasticity. Now, if this begs the question, okay, I have some component which is opaque, which doesn't allow light, then can I apply photoelasticity? It turns out that if we were to apply a coating, let us say that we again have that same component, but this is opaque now. So what we will do is we will take a coating and we will apply it over this. But that coating is transparent. The coating is having properties of photoelasticity. Now what we will do, similar to strain gauges, we assume that once we have coated the material with that coating, photoelastic coating, whatever surface strains are there on that material by virtue of that being loaded, by virtue of this disk being loaded, whatever are the surface strains are faithfully getting delivered to this coating. And this coating will start showing patterns, which we can again observe through one particular light optics. So that variant of photoelasticity is called reflection because we are not allowing the light to pass, but we are actually impinging the light from the front and seeing it from the same side. So that variant is called reflection photoelasticity. So much for these two. These two are the variants. So as we saw, one is actually stress based because it is giving sigma 1 minus sigma 2. One is strain based in the sense that the surface strains of the underlying opaque material is getting transferred to the film, to the coat that we have given, and the coat is actually showing some photoelastic response. So this is essentially strain based, and naturally we will be seeing the entire field. So the whole field we will be seeing, and this can also be helpful in measuring strains. So photoelasticity is a candidate for now. It is not a candidate that is ruled out. So let us keep this. Now let us go divert our attention to this method called digital image correlation. Why these things are important, one might wonder in a subject of strength of materials where we are simply studying stresses, strains. The thing is, we generally study these topics in isolation, but we are not able, generally, people are not able to, they find it difficult to put it together in the context of a problem as to why we are studying this. The basic idea behind studying this is to be able to design components. For able to design components for complex problem, we need to conduct experiments also. We should know how the stress flows are, what assumptions go into this. So in order to get an overall picture as a designer, the course has been devised in such a way that we will take slight detours here and there into experimental results, into experimental methods, what we are measuring. Because we want to, when we say strain or stress, we want to know everything about that right from how it is mathematically expressed, how it is mathematically manipulated, how it is used in design, right to how it is measured. So we are presently looking at how things are measured. So photoelasticity, I have explained. So let us look at what digital image correlation is. Now, let us say I have the same body, or let me take a uniaxial tension specimen, all right? And I subject it to a pull at either ends. Naturally, what will happen when it gets pulled after some time, it will be elongating like that. Let me move it here. Just for the sake of this example, I am showing exaggerated displacements. I hope you can appreciate that. So what has happened? This has contracted because of Poisson's effect, and this has elongated. Now, my idea is if I put some point, let us say I put some pattern here, some random pattern, which are called speckles. And I have cameras that actually look at this. So at each and every time step, using algorithms, I can actually track, for example, let me confine my attention to this speckle over here. So after some time, it would have gone here. So my idea is to be able to map this to this. So by this way, it won't be side by side naturally. I hope you can understand that it will be over this only. Once the experiment is done, I am drawing it side by side, but it will be overlapping. So my idea is, if I know the final position of this point with respect to some datum and the initial position, so final minus initial gives me displacement. So this is a way of measuring displacements. How? By putting some patterns, random patterns on a surface, loading the specimen, recording it by a camera, and then extensive image processing is involved, where images of the speckles will be correlated by algorithms, and that will actually track each and every speckle as to where it goes. So this is the principle behind digital image correlation. And it turns out that in terms of measuring displacement, DIC as it is called, is better, much better than our reflection photoelasticity, because its response is not very strong as compared to the transmission part. If we see the reflection part, the response, the fringes will be very feeble. Whereas here, the principle itself is very different. We make speckles, we are tracking the speckles. So this is quite extensively used in measuring whole field displacements. Once we get displacements, we saw yesterday that we saw in the previous session that once we get displacements, we can maybe fit a curve, get a displacement field, take its derivative. Well, what will its derivative, the gradient of the displacement field will give us strains. From strains, using constitutive relations, we will go to stresses, integrated back to this force which we applied. And we know everything about the problem. This I have explained in the context of a simple tension test. It could be a very odd boundary with odd kind of loading with along different axes. So the complexity of the problem can be much higher than this, in which case we have to resort to these experimental techniques for making our measurements. So I hope that is clear. So although for this question, photoelasticity was a candidate which can measure whole field strains in the form of reflection photoelasticity, but digital image correlation will be more preferable here because it is best suited for measuring for displacements. From displacements, it can measure strains by taking the gradient. I hope it is clear. Are there any questions at this point? Okay. So, all right. I take it it is clear. So, what we do is, let us say we have it like this. So, we will have two cameras placed like that. Let this be considered a camera for now. So, we'll have two cameras, one like that, and the other one will be placed like this. So, with both these cameras, we will be looking at the same image. It works on the principle of stereoscopic imaging, which is similar to our two eyes. We see from the two eyes, we see at one point. It works on a similar principle in order to derive the displacements, out of plane displacements also. The depth also gets captured here. So this is the basic of DIC. So let us look at this question now. One minute. Yeah. The resultant tangential strain epsilon theta theta or epsilon theta, because it's a repeating subscript, so that is dropped. In polar components due to displacements u and v is given by what? It is in the polar coordinate system. Now in the last session we saw one displacement which was given by ui plus vj, where this u and v were some functions of x and y for a coordinate system like that. So we have a coordinate system x and y. Rather, let me not write x and y, I'll write I and j. So these were my For this coordinate system, there is a vector. There was a vector which we resolved like this, like that. So this is u, this is v, and this is the vector d. In my xy coordinate system, I have resolved that into u and v. I got this as the displacement field, which were some functions. And then we saw that strains is the gradient of that displacement plus its transpose by 2. Excuse me. Where it gave the relations dou u by dou x, dou u by dou y plus dou v by dou x, and it was 1/2 of this. Similarly, this was symmetric, as we remember, and the fourth component was dou v by dou y in the plane, essentially in the xy coordinate system. Now the question says it is the same displacement vector, but it is not represented in the xy coordinate system, but instead in the r theta coordinate system, the polar coordinate system. So let us see how to go about doing that. So let me take the same thing, only this I'll remove the unit vectors, but instead my unit vectors are something like that. And for the sake of this thing, I will express the unit vector in the r direction as er cap, and let this be e theta cap. Fine. So the same this thing, when I had x and y, I had resolved this into u and v. Now I can do the same thing here also. Only this will be my u now, u, and this will be my v. But I have to differentiate between xy coordinate system and polar. So what I will do, I will mark this as ur and vr, just to identify that they are just with the subscripts r, to identify that they are with respect to the cylindrical polar coordinate system. Fine. So what do we have here? We have this is I, this is j, and then I'll put this in some other color. This is er cap, and this is e theta cap. And let this be oriented at some angle theta. All these are unit vectors. So I can write er as cos theta I plus sin theta j. Similarly, I can write e theta as minus sin theta I plus cos theta j. Now, when we were representing this in the xy coordinate system, and when we were taking derivatives of these, the derivative of the unit vectors were not coming into the picture because unit vectors were constant. In the Cartesian coordinate system, the xy, no matter where we place it, it will be constant. Its the time rate of its change with the spatial coordinate will be 0. Its derivative is 0 essentially. But same is not true for our cylindrical polar coordinate, which is what leads to the addition of certain terms in our in our calculations. So if e theta is this and er is this, now we know that these are unit vectors. So essentially the radial direction, the length is fixed. So no matter how we transform it, its length is not going to change. So what is another way of saying that is that dou er cap by dou r is 0. Similarly, dou E theta cap by dou R is 0. Now let us see, we have seen how it changes in the radial direction. There is no change because it's a unit vector. But what will happen when we take the change with respect to the angle? So let us see that. So this is ER. So if I were to calculate dou ER when I change my angle, so what will this come out to be? This will be minus sine theta I cap plus cos theta j. I've just differentiated that. But we already saw minus sine theta I plus cos theta j is our E theta. So this gives us an important result that dou ER cap by dou theta is nothing but my E theta itself. So this is one result we have. Granted, many of you might already know this, but I'm just going in detail just for the sake of being a little complete. Okay. Similarly, I have my E theta here. I'll take dou by dou theta of E theta cap. This will come out to be minus will still remain the same, minus cos theta I, and this will become minus sine theta j. Now if I take minus outside, it becomes cos theta I plus sine theta j, which happens to be our ER itself. If we see from here, it is the same as ER. So we have seen that in the cylindrical polar coordinates, or rather in the polar coordinates, because we are not going out of plane presently. In the polar coordinates, my unit vectors change with the change in the coordinate directions, coordinate system. So we have got this. So far, so good. Now, what we did earlier, now let the displacement field in polar coordinates be given by, I'll say d. Let us take the same symbol, only let this be UR ER cap plus U theta E theta cap, or let me say V. See, here we were taking this to be UR and VR. Just to differentiate, what I will do is let this be U, let this be V. Uh, okay, let it be like this, fine. So this comes out to be UER plus VE theta. Remembering that U and V can be functions of R and theta because it is naturally represented in the R theta coordinate system. It is a displacement field, so it can be functions of R and theta. Fine. Now in our x y coordinate system, what we did, we simply took dou by dou x I, dou by dou y j, and then we operated it over u and v, where I and j, these were not changing with our coordinate system, but here that will not be the case. So here the gradient operator in the polar coordinate system is dou by dou r er and dou by dou theta e theta. But since we are taking this with respect to a spatial coordinate, theta, as we know, it is a dimensionless quantity. So that is why it will be 1 by r times of that. And this can be derived, but I don't want to get into that. Basically, this is my differential operator. This is my del operator in the polar coordinate system. So, and my displacement vector is given this way. Displacement field is given this way, right? So let us operate this and see what comes. So what we are getting is dou by dou r er cap plus 1 by r dou by dou theta e theta cap. Well, essentially these relations, the strain displacement relations in the polar coordinates has already been derived in the lecture from geometry. I could have just passed on this question by stating what is the correct answer, but that would not be very intuitive. So what I'm trying to do is to impress upon the fact that in polar coordinates, there are some additional considerations that we need to take care of. It is not just as simple as we do in Cartesian coordinate system where the unit vectors don't change. Here we saw that the unit vectors basically have some influence on the results, which leads to the addition of certain terms. So I'm just trying to show how that terms are coming about. Granted, this will not be complete in a sense, but it will be enough to get things clarified for now. Okay, and I have to operate it over this. So let me do that. So this will be, let me add the page here, and it is just a product rule. Here on now, we are just going to apply the product rule systematically and see which are the components of the tensor that are coming about. So dou by dou r of u er cap er cap. So what I've done is here I have just placed this thing. I have multiplied this out. When I multiply it with the operator, it essentially operates on the operand. This is plus 1 by r dou by dou theta of u er, or rather let me not write it like this. Let me maintain the same colors so that it becomes easier. Okay, then I have plus this quantity. I'll move this, I'll bring this back again. Plus, again, I have to take this for the second term. Plus this, move this and bring this. I hope there is no difficulty in following that. Now we just have to apply the product rule systematically. Now we saw, so this first term will give us, let me move it here, the first term will give us it will be dou u by dou r er. Now this is not a dot product. This is not to be considered as a dot product essentially. What this implies is if I have a strain tensor in the r theta coordinate system, so the first term we know is we'll be having the subscripts rr, then there'll be r theta, theta r, and theta theta. So it comes from the principle of tensor products. So wherever we see these components, we have to identify that RR. So whatever is the coefficient of that will sit in the tensor at that point, at that place. So that is how this is supposed to be interpreted. Don't take it to be dot product. All right. So with that explanation, so I have differentiated the first term. I have to differentiate the second term also because we are applying the product rule. So u will come out. So u, this will be plus u, or let me write it in fact, plus u dou by dou r of er cap, er cap. Fine. Now I'll write the second term, 1 by r dou u by dou theta of er e theta plus 1 by r. U will come out. So it will be plus u by r dou by dou theta of er, and we have e theta cap as always, plus dou v by dou r. I would encourage the viewers to work this out on your own so that you are familiar with this and doesn't look like some this thing I'm writing. So v comes out dou e theta cap by dou r er cap, plus the last term I have to expand it out. So last term will be 1 by r dou v by dou theta e theta plus v by r. V comes out, and then this will be dou by dou theta of e theta e theta. Now it is just a matter of simplifying based on what we already know. We know that any unit vector's the derivative with respect to r is 0, and we know these two things. So let us apply that systematically. So the first term comes just like that. So this gives us, so this is the next step. And I know that this is 0. So that term completely goes to 0. So that I'm not taking. So this goes to 0. The second term, this comes just like that here. And then I have ER by dou ER by dou theta. What was dou ER by dou theta? It was nothing but E theta we saw here. So I will just substitute that. So this term comes here. There is a plus here. And then there is this term. But this I already know it is nothing but my E theta. So my E theta comes again here. So I have accounted till here. This component, it just like that it comes. And then I have something with respect to R. We again saw that this is nothing but 0. Then we have this component coming here. And then the last component, we saw it is dou E theta with respect to E theta, which was, I'm sorry, I missed out the minus here. It should be minus. Please take note of that. I had missed this minus out. So this will be minus ER. So it is nothing but this quantity. I have to bring it here. In this, I will erase this and put it as minus ER. So this becomes minus. This becomes minus. This is ER. So this is my last quantity that comes there. I hope that is clear. We have just applied the product rule systematically, and we have written down the quantities here. Now it is just a matter of grouping them together with respect to this, and we will get how our displacement gradient looks. So this gives us ER. If I were to group, there is only one term. There is only dou U by dou R. Now ER E theta, if I were to group ER E theta, there is ER E theta, there are two terms. This is what I was saying, that there are additional terms coming in. Now why this is minus? I hope you are able to see that this was plus, there is no minus here. This is positive only. So let me group this. So I have this plus this minus V by R. I have grouped this term and this term together as ER cap E theta cap. So two are done. Next is E theta ER. ER E theta we have done. E theta ER we have to do. E theta ER. There is only one term again. So this will be plus dou V by dou R E theta ER. And then I have the last term where there is E theta E theta. So I can see that there are again two terms there. So let me group them together. So I have plus U by R and I have this quantity as an addition here. This is E theta E theta. So far so good. Now based on what we discussed about how to identify these, I will write the displacement gradient in a matrix form. So the displacement gradient based on this, we can write the displacement gradient in matrix form, or rather as a tensor, so to speak. So my displacement gradient, let it be called H again, will be, what is the first term? First term is the coefficient of ER, which is just this, fine. The second term is R theta. So it is this coefficient. It comes here. The third term is theta R, which comes there. And the fourth term is this quantity, which comes here. So we saw that it is a bit different from our displacement gradient. I have not written that down. My displacement gradient in my xy was simply dou u by dou x, dou v by dou x, dou u by dou y, dou v by dou y. It was as simple as that, with the understanding that here u and v were represented in the xy coordinate system, which were functions of x and y. But now we have moved on to polar coordinate system, where our displacement gradient has come out like this, with the understanding that here u and v are functions of r and theta. I hope that is clear. There is no confusion here. So now we have actually derived the displacement gradient. It is just a matter of applying what we already know, which is strain is nothing but my displacement gradient plus its transpose by 2. So let us apply that. So the strain in the cylindrical polar coordinate system will be, transpose means uh, something plus its transpose by 2 means only the cross diagonal terms will get affected. This will just get added up twice and get divided by 2. So it will just remain the same. So my cross diagonal terms remain the same. These two get added. So this will be 1 by 2 of dou v by dou r plus this quantity. And we can clearly see that it will be a symmetric tensor. Tensor is symmetric. So the same thing will come here also. Same is not true about the displacement gradient, mind you. So this is my strain tensor in the cylindrical polar coordinates. Whatever was derived in the lecture based on geometry, we have simply applied the product rule with the understanding that the under transformations, ER cap and E theta cap change when differentiated with respect to theta. Based on applying that, we have arrived at our strain tensor in the r theta coordinate system. So from here, we can easily correlate now. This is nothing but epsilon rr, epsilon theta theta, epsilon r theta, and by equality of this thing, by this being symmetric, it will be one and the same. So now let us revisit our question, what it asked. It said that they want the resultant tangential strain in the polar coordinate system due to the displacements u and v, where which is represented in this. So what we are looking for is this component, which is nothing but u by r plus 1 by r dv by d theta. So let us see which is the option, u by r plus 1 by r dv by d theta. So this is the correct option. I could have just said that and moved on, but I thought it will be better to derive it from another perspective and see why these additional terms comes about. So I hope this is clear. So are there any questions at this point? Is it clear what we discussed? Okay. All right. So this is now we are confident in applying this also. If we are given in a cylindrical polar coordinate, we are given some displacement field, let us say this is r cube theta squared er plus 1 by r theta cubed, or rather why limit just to this? Let this be sine theta e theta. Some random displacement field if we are given that a body is undergoing this displacement field. From here we know how to calculate our strains because the coefficient of ER, this r cube e theta is my u, this is my v. I have what I have to do. I have to take partial derivatives. And if I have to find the strain at some point, the coordinate of that point in r and theta, I just have to plug it back and I will get my strain tensor. So this is the application part, although there is no question I have on application, but I hope there shouldn't be a problem now that we have derived it when it is just direct application. All right, so let us move on to this question. Choose the correct answers regarding the measurement of strain. Digital image correlation is a full field technique used for stress measurement. So we saw it is not directly stress because it is actually correlating one point, one speckle to the that is, it is temporally correlating, a time varying correlation in order to arrive at the displacement. So it is not a stress measurement, so to speak. It is a displacement measurement technique. Now one might say from displacement we can come to strain and stress, so it can be considered as stress measurement. That is derived, that is not a direct quantity that we are measuring, so it is not stress measurement. Strain gauges essentially measure component of strain at a point. Yes, we saw in that example where the person had pasted the strain gauge on the composite beam. We saw it was pasted at a point and it was measuring the component along its length, gauge length. So strain gauge essentially measure component of strain. Yes, speckle formation plays an integral part in digital image correlation. This happens to be true because as we had discussed when I just gave a brief intro, it turns out if my speckles are very uniformly spaced, it is a problem for the system algorithm to correlate because there has to be some randomness for it to identify different speckles. If all are identical, then it is a problem. And the distance between the average distance between each speckles decides my resolution. Up to what minor strains can I measure? So these things play a very crucial part, which is discussed in the lecture also in detail. So this happens to be true. This is just some information that we are gathering. DIC measurement relies on tracking intensities from a group of pixels between deformed and reference images. So in the context of our previous discussion, this will be our reference image. So initially when I start out the test, just when I'm starting, before this load is applied, I will take an image of this. Then I'll apply the load and keep on taking images. So the starting image will be my reference against which my future acquired images will be compared so as to measure the displacements and strains and so on. So DIC, yes, this is true. Strain gauge can directly provide both displacement and displacement gradient along a specific direction. It doesn't work on that principle. It cannot provide displacements. It can only provide the strain. The strain gauges can only measure the at that point what is the change, spatial change of the displacement, so to speak, if you want to say. So this is not true. I hope this is clear. If there are any questions, please feel free to ask. Okay, in the meantime, we'll move on. So this question says, choose the correct sequence of steps followed in the strain measurement of a material sample using DIC, digital image correlation. Identify the sequence in the correct order. So what are the activities that one needs to do? Uh, it is better that we also get exposed to these things rather than just applying one formula so that there is some level of interest in the subject. So A says image data acquisition, selection of camera and lens and lighting. Yeah, one thing I forgot to mention here was we cannot simply take the images like this. It has to be well lit. So there will also be lights, LED lights. Or how do I put a light source? Okay, I hope that is clear. So this is a light source. So essentially we will be having light sources. We have to illuminate the speckles better in order for the image acquisition system to see the contrast. So basically how we will be putting the speckles is we will have a white coat on the specimen and then we will spray some black speckles on that. So the difference between that white and black intensity, the better it is, the better the system will be able to capture the contrast and identify that marker or the speckle. So that for that lighting becomes very necessary. So in the context of this question, selection of the camera, lens and lighting needs to be done. Okay. Temporal matching. Temporal is just a fancy word for time varying matching. With varying time, we match something is temporal matching. Spatial, temporal. There are only two types of coordinates. One is a spatial coordinate, one is a time coordinate. All our problems are confined within these only. So this is just a temporal variation, time variation. Then strain measurement, comparison of the deformed and undeformed images, and displacement measurement. So initially what we will do, we will first start out with our take our problem. We will have to select what kind of this thing we want. I have to select my camera. 1 minute. I'll take a better snip of this. So first step is I select my camera. Then I actually capture my images using that camera. Then I compare the images which I captured with some reference image. So that will give me, based on that comparison, I will be doing some temporal matching, and from there I will be getting my displacement measurements from one frame to the other, how the point has moved. Final minus initial gives me my displacement measurement. From my displacement measured, I know how to calculate my strains, which we have seen in excruciating detail now. So these are the order of the steps that make sense. If you are not in agreement, you please feel free to prompt as to why what is not clear, and we can talk about that. But essentially, this is the broad uh, steps we have to follow in order to make the measurement using DIC. So I leave it to the viewers to select the correct option. All right. So let us move on to some other next question. Choose the correct statements. If a specimen does not return to its initial shape or length upon removal of the loading, it is considered to be responding elastically. So I need not delve much into this. You can see why this is not correct. And another misnomer, I'm just generally stating, another misnomer that we have is we call a material elastic. A material need not be elastic or plastic. Essentially, the process is what makes it so. So I can have one material. I can have one material which, if it is loaded less, responds elastically if the process is within its limits. Whereas if it goes beyond its limits, it becomes plastic. The process is what makes it elastic or plastic. Up to what load I am essentially loading it. So the same material can behave elastically or plastically depending on how much we are loading. All right. The gauge factor of a strain gauge is experimentally determined by the manufacturer for a uniaxial stress field in a particular batch. So I'll just delve a little bit into what this means. What is this gauge factor? Let us just see that. So we have our strain gauge like this. I am drawing a blown up diagram of a strain gauge. I'll have the gauge here, and I'll have two soldering tabs here, which will be connected like this. So the example which I showed where the person connected, they will be essentially soldering wires to this and connecting it to the Wheatstone bridge. And here is where this will connect to a metal foil. That foil will be in the form of a grid, because for measurement of the resistance we need a huge length, but we also have a necessity to measure the strains at one point. So we want to confine that length into one closest to a point. What is the best way to do it is to put it in a form of a grid. So that is what we do. Now the gauge factor, essentially our change in resistance, if we see, is change in length by length. So this is what we define as the gauge factor. So what normally the suppliers do is they will take the same cantilever beam, they will paste this, they will plot, they have a controlled experiment, so they know what is the change in length they are introducing. And they will see how much the resistance is changing for that particular resistance of that strain gauge. And they will plot a curve and essentially arrive at this value. And this gauge factor they will give as a part of that batch. When we buy the strain gauge, it will come with a pamphlet which will say how the calibration was done and what is the gauge factor to be set. So when we see this setup, as we saw, it will not be looking like this. All this will be confined within a, an amplifier inside, where we have to just connect these tabs. Those amplifiers are also shown in the lecture. So once we select that, we have to select the appropriate gauge factor in that mission. So that gauge factor is what the supplier provides, and how the supplier arrives at that is by carrying out an experiment himself at their end. The manufacturer does it at his end and does it. And it is a function of the batch also. So whichever batch we have taken the strain gauge from, there could be variation. So it is very important that we identify that value correctly and enter it for precise measurements. Transverse sensitivity factor KT is the ratio of transverse sensitivity to. So the sensitivity of a strain gauge essentially is axial strain, how much it is sensitive to axial strain, how much it is sensitive to transverse strain, and how much it is sensitive to uh, shear strain, axial, transverse, like that. This essentially won't be much, that is fine. But what happens is when I have a wire like this, I'll just briefly explain what this is. So this is how my grid will be connected. For the sake of this example, I'm just taking a grid like this. So there'll be many coils, and this is what will be inside in here, which will get connected to the soldering tab. That is how a strain gauge is constructed. Now, when I have when I have a pull in this direction, naturally these lengths will increase. But we saw in a component, when I pull it, if this is pasted onto a component, let us say, and I minimize its size like this, initially it is like this. Now when I pull it, it will become like this. So there will be a transverse on the vertically also, it will reduce because of the Poisson's effect. So what will that do? That will reduce the length of this. But we are measuring only along the length. We don't want that to come into our picture. So what they generally do, the manufacturers do is they will make this very fat, very stub. The ends will be thicker. Why? Because from our high school physics, we know that resistance is rho L by A. So if I change my area of cross section to a thicker one, my resistance, the it reduces. A is more means R is less. So change in R will also be less. So it will not essentially pick up those signals. If I make it thick, area of cross section becomes wider, and that portion's resistance comes down. So that is how this is done. But nonetheless, these will also bear some, this will creep into our results, which is why we define something called a transfer sensitivity, which is the ratio of these two, which is the ratio of SC and ST. So how we will define that is, let us say this is my total, this thing, total change in resistance, delta R by R. So what we will say is delta R by R is nothing but S SG into epsilon A plus ST by SA. I'm sorry, not SG, SA. I'll take SA common, that's all I'm doing. Plus ST by SA into epsilon T. And when this also comes out, SA epsilon A comes out, what happens? 1 plus ST by SA into epsilon T by epsilon A. So there will be some effect of Poisson's ratio also. So this factor is what is called as the transfer sensitivity factor. And for one particular batch, for a particular grid design, they will be defining this as to what this is. Reflection photoelasticity is an extension of photoelastic analysis for the analysis of opaque prototypes. As we saw in the initial preamble where we discussed this, we saw that reflection photoelasticity, we basically coat the material with uh, a coating which has the photoelastic property, and then impinge light on it and apply the same principle of photoelasticity, which gives us freedom to apply this not necessarily to objects which are transmitting light or transparent, but also to opaque objects. But only this works on the principle of compatibility of surface strains between the opaque object and our coating. I hope that is clear. Okay, so let us look at this question now. Are there any questions at this point? Okay, all right. Granted, this session might be a slight detour, not fully dealing with the, uh, very fundamental mechanics, of this thing. But we are taking slight detours into strain gauges, DIC, optical techniques, and all. But rest assured, very soon we will get into the beams and torsion and things like that. For those who are attending with the anticipation that why we are not discussing that, we will get back into that very soon. But that is something you will already study in your strength of materials course. There must be some additional information that this new course has to offer, which will actually help you link, uh, actual design with what you are studying. So that is the essence behind it. I urge you to take it with that spirit. All right. So this says Arun conducts an experiment to measure the strain on a cantilever beam. As we see, there is a cantilever beam. There is a cantilever beam in this figure. He applies a load of 10 Newton. So this is the top view. Mind you, this is the top view. And when we see it from the side, this point comes like this. So I hope that there is no confusion on that. So what Arun has done is he has pasted both the strain gauges on the top side by side, symmetrically about the center line. Fine. He applies a load of 10 Newton on the cantilever and supplies. And what he has done is these two strain gauges, as we saw earlier, what he has done, he has soldered this. So this strain gauge is not in isolation. It is actually pasted onto the beam. The beam is not shown there. I hope that is clear. And he has supplied 5 volts on an initially balanced bridge. He has supplied 5 volts of voltage to measure the strain using the strain gauges 1 and 2. With the provided details, answer the following question. To maximize the signal output of the bridge, select the most suitable pair of the following options. Strain gauge 1, 2, 3, 4. SG 1, 2 means strain gauge. R 3, 4 means the bridge resistance. These. So okay. I'll just slightly explain this. Not in much detail. I'll just show you how the formulation comes about. So if this is the strain gauge, let me call this R1 for now. Let me call this R2 for now. R3 and R4 are anyway there. Let this be A, B, C, and D. Now voltage across BD is my output voltage. That is E. So this will be nothing but voltage AB minus voltage AD. Now what would voltage AB be? AB will be some ratio of this V. That ratio will be dictated by R1 upon R1 plus R2. This times V is my voltage AB. Similarly, voltage AD is R3 upon R3 plus R4 to V. So now that this is there, I know the individual voltages across the branches, and what I want to see is what is the output voltage for a given V. That is the entire point of my analysis. So if I substitute, this will come out to be R1 upon R1 plus R2 minus R3 by R3 plus R4 into V. This is my output voltage. So if I were to cross multiply this, let me just do it quickly. R1 R3 plus R1 R4 minus R1 R3 minus R2 R3. Okay, by this thing. I'll just take it from here. I won't write it again. Into this. And we can see this anyway cancels out. These two cancel out. So my expression comes something like this. Into my input voltage. Whatever I gave as my input, it will change as per this. So if initially when there are no strains, I want my Wheatstone bridge balanced. I don't want to I don't want any current to pass through that. So that when I actually stress the object, when I actually apply the load, there is current passing and I make only that measurement. So for initially for this to be balanced, what is the condition? My E should be 0. It should not read any output voltage. So for E to be 0, for the initial balance, E to be 0, this is the condition. This has to be 0, which means this ratio has to hold. If this holds, then my bridge is balanced. Fine. So this is my initial condition. Now I have to see with the change on every resistor, how my output voltage will change. So I can see from here, I'll just say from this expression, I can see that E is a function of, it is a function of R1, R2, R3, R4 and the voltage. But voltage we will be keeping constant. The excitation voltage we will keep it constant. And we want to see how E will vary as Ri, where I changes from 1 to 4 varies. So how can this be done? For we know from basic mathematics that for a function, for a parameter that is a function of multiple parameters, how do we find the its derivative with respect to each? It is nothing but the total derivative. I hope that is clear. So what we will do is dou E by dou R. I is nothing but sum of this dou R actually. I'll just write it out. So it will be dou E by dou R1, E by dou R2. So this is what it will be. So if I take the partial derivative of this, I won't get into that much of mathematics. If I take the partial of this with respect to R1 plus this with respect to R2, and then I apply my initial bridge balance condition, I will get a neat expression for my change in voltage. This is nothing but change. What I have written here is change in the output voltage with change in the resistance, how it changes. So the output voltage will come out as R1 R2 by R1 plus R2 squared into change in R1 by R1. So I'm just mentioning how this is derived. If you are interested, I would encourage you to derive it on your own and see. Nothing, we just have to take the partial derivatives, do a little bit of manipulation, and we'll get here. R4 into V. So this is what it comes to. Uh, I am a little bit unclear about the exponent here, that you can just verify. But anyway, our main interest is to see how the voltage changes with change in these resistance. So this is the grand equation that we have for our strain gauge analysis. Now in the context of our problem, we see that R3 and R4 are not strain gauges. They are fixed resistors in the bridge. So that is not going to change. So R3 and R4 doesn't come anyway. Before that, if you want to address the first question, what it says is how to maximize the signal by suitably selecting these. Now it turns out I want to maximize my output voltage E. How should I select my resistors? So if I take R1 by R2 to be some value M, naturally from here R3 and R4 also I can relate to that M. So if I recast this in terms of that ratio R1 by R2 and take the partial of my output voltage with respect to that M, the curve what we get with respect to M and the output voltage, it turns out it is something like this, where this peak, as Mr. Jayakrishnan will also add, this peak will be at M equal to 1. This is derived in professor's other lecture on experimental stress analysis, but since this course is not for that, I'm just mentioning this as a statement of fact. If you are interested, you can go watch that lecture once. So when R1 by R2 is equal to 1, we have maximum, we have uh, the output signal maximized. That is dou m by dou a equal to 0. In order to find the maxima, that is what I'll do. It turns out this is so. And we already have this condition, which implies, which collectively implies that will give me the maximum output. So here, if I select all the resistors to be of the same resistance, it will maximize my output. So far, so good. Now, let me take this equation in the context of our problem and look at it afresh. So in the context of our problem, we don't have any change in R3 and R4. R3 and R4 don't change. So I'll straight away remove that from my equation. Only these two change. So now let us see what the question asks. So where is the question? Question is over here. After selecting the best pairs of the strain gauges, so he has done that analysis and he has selected 250 for all because that was the only option having the same resistors throughout. He connects the strain gauges to the Wheatstone bridge as shown in the figure, and he energizes the bridge by 5 volts. So the input voltage V that he gave was 5 volts. And the change in the resistance in the strain gauges is measured to be 0.1 ohms. What will be the reading of delta E is what is asked. So this is 5, this is 5. We already know R1, R2 are all 250. The change in resistance, he has measured it to be 0.1 ohms. Now let us see how he has connected it. I have to take the entire thing only there. So he has connected it this way. Both 1 and 2 are placed side by side on the top. Now, granted, we have not studied bending yet, but nonetheless, we can at least get a feel of this, that when we press this like this, both will get extended by the same amount because of the symmetry and the placement of the strain gauges, right? So delta R1 and delta R2 are both same, identical nature. Both are getting pulled, elongated. So both delta R1 and delta R2. So therefore, delta R1 equal to delta R2 equal to plus 0.1 ohms. Both are getting elongated. Just 0.1 ohms. And the voltage is 5 volts. Input voltage. Let me say in, V in. Alright. And then R1, R2 is 250. So what does this come out to be? We can see that if this is 0.18, this is 0.18, it cancels out. So what does that imply? The reading what he will get is 0. What he will notice is, although he is pressing, he is applying the load, he is not, the reading in the strain gauge amplifier is not changing. That doesn't mean that the material is so strong and it is not, getting strained. It implies that there is something fundamentally incorrect with the connection, because he has put it on adjacent arms of the strain gauge, and adjacent arms actually compensate each other. They subtract out any effect. So what he should have done is, he should have placed it in such a way that it adds up, which means he has to place the similar kind of uh, strain gauges recording similar kind of strains. He should put it in opposite arms rather than adjacent arms. So here E was 0. He did not measure anything. Then he woke up. He realized that after some ambiguity in the strain measurement, he swapped the connection of the Wheatstone bit to achieve maximum sensitivity with two strain gauges. When will we get maximum sensitivity with two gauges? Let us say that I connect, rather than connecting it here, I connect it here. So R1 and R3 become strain gauges. R1 and R3, which add up. And these two will anyway go to 0. So in such a case, it will maximize the output. So in that case, he'll remove this, and he has placed it this way. Need not be R1 and R3, it could be R2 and R4 also. What I mean is, it is essentially in opposite arms. In such a case, what is the value he will read is what is asked. So let us see. It is not a gradient of E. Mind you, it is delta E. It is a, I suppose you get the idea. So this will come out to be what? 250 into 250 by 500 squared into the same zero point 0.1 ohm is what is applied. 0.1 by 250 plus 0.1 by 250 into 5 volts. So what does this come out to be? 0.2 by 250 by 500 squared into 250 squared into 5. So this comes to 1 into 10 power minus 3 volts. Answer is asked in millivolts. So essentially E, that who is this? Arun. Arun will be recording a output voltage of 1 millivolt. And in the strain gauge, according to the manufacturer, as we saw, he will be entering the gauge factor the transfer sensitivity, this and that. So finally, it will automatically get calibrated to reflect the strain. This value, the machine will automatically calibrate it so that whatever the value he reads, it will directly give him the strain for this problem. For this problem, he will directly get the strain at that point. And we will see in the when we come to beams, we will see actually what that value should be based on our bending theory. I hope that is clear. Are there any questions at this point? Okay, I take it is clear. So let us move on. So we have a rectangular rosette measuring strains 300, 400 and 500 microstrain in strain gauge A, B and C. So we have A, B, C, where B is oriented at 45 to A and C. So let our XY coordinate system be like this. X, Y. So A, B and C report the following quantities with respect to the XY plane. Neglect transfer sensitivity effect. What they mean is the strain gauge has measured the strain. Neglect whatever these cause. You just take that to be the actual strain at that point and give me the answer is what the question is saying. So we will do that. So epsilon A, here we can see that epsilon A is 300 microstrain, which is same as epsilon XX because it is parallel to the X. Similarly, epsilon C is 500 microstrain, which is similar to epsilon YY because these two are parallel. I hope there is no difficulty in seeing that. Now, epsilon XY at this point, we don't know. And mind you, all these three strain gauges are trying to measure the strain at this point. Since it cannot be put one over the other in some specific problems. So this is how generally it is measured. This distance is kept to a minimum, but nonetheless, it is trying to measure at this point. Please keep that in mind. And we don't know epsilon xy is what we are supposed to find. So we have two strain components. We don't have the third strain component, but we have what it transforms to. Epsilon B is 400 microstrain, which is nothing but epsilon x prime, right? Where we rotate by 45 degrees. We know we have our strain transformation relations at our disposal. So we can do that rotation and see what will come out to be. So we know that epsilon x prime is given as epsilon x plus epsilon y by 2 plus this will be minus cos 2 theta plus epsilon xy sin 2 theta. So this transformation equation we already know. It is just that matrix multiplication cos theta sin theta minus sin theta that you can simply do and find out. So I just have to plug where theta is 45 degrees. So 2 theta is 90. Sin 90 is 1. Cos 90 is 0. So epsilon x prime when we rotate it by 45 degrees, I will reach this direction and that is what is given to be 400. So I just have to plug it there. So 400 microstrain is nothing but epsilon x, which is 300 plus 500 by 2 plus 300 minus 500 by 2 cos 90 plus epsilon xy sin 90. So this leaves me with 400 equal to 800 by 2 400 plus 0 plus epsilon xy. What does this give me? Epsilon xy is 0 at that point. At which point? At this point. Epsilon xy is 0, which means gamma xy is 2 times of epsilon xy, which is 0. So if shear strain is 0, what does that imply about the normal strain in that direction? It is the principal strain. So we have these two as principal strains. So therefore, principal strains are epsilon A, which is 300 microstrain, and 500 microstrain. Now again, according to our naming, we will name epsilon 1 as the algebraically larger one as epsilon 1, and epsilon 2 is 300 microstrain. So this much we have done based on our analysis. And by the way, I did not delve into that. This rosette, basically we saw how one strain gauge functions, but since our strain tensor, we need three independent components, epsilon x, epsilon y, epsilon xy, in order to populate our strain tensor. So minimum three, we at least three strain gauges we need where we don't know the principal strain directions. So that is why these come pre-attached like this in different configurations. These are called rosette, strain rosettes. Fine. Okay, so from here the maximum principal strain is what? It is 500. The minimum principal strain is 300. Okay. I hope this question is clear. If there are any questions, please feel free to ask. In the meantime, I'll move on. Let us look at this question also. A tensile test was conducted on mild steel specimen. So we have been given that it is a mild steel specimen. So what do we know about mild steel? We know that it has a clear yield point defined, whereas high strength steels don't have that, which is why we go for that 0.2% offset strain and so on, proof strain and so on. So the curve will be something like that. So we'll have one point till where the proportionality holds, that is it's linear. Then we'll have a slight kink. So we'll have a slight kink, or rather let me put it like that. Then we have the upper yield point. Then I have some other color I'll take. Then I have the lower yield point, and then it goes like that. There'll be a strain hardening phase. Then I'll get to the maximum, the peak ultimate strength, and then it will go falling like that. At which point it will just the material separation will happen. So this is my stress strain curve essentially. But in the question, let us see what is given. It says the load at proportionality. The load at the proportionality limit is 150. So this is my stress strain curve. Now let me draw the load versus displacement. I'm just putting it as delta. This is load. So when it goes straight like that, this is my limit of proportionality at the, in fact, let me take this itself. I encourage you to think over whether these two will be the same or not. Anyway, for now, this, the point at which this is coming is given to be 150 kilonewton. Okay. extension of the load at 40 kilonewton. So there is some load at, if this is 150, here we'll have 40. So at this 40, I have my extension. This is given to be 0.1 mm. All right. Then load at the yield point. So let this be the yield point. So the load here is 175 kilonewton. And then at the ultimate point, the load is given to be 261. Okay. Extension of the rod at load of 175 is 0.62. So it is just a matter of mapping it onto this thing. So this is given to be 0.162 mm. 0.62, I'm sorry. 0.62 mm. And what else is given? Peak load is given to be 261, which I've written. Total elongation of the rod at the end of the test, at the end where it broke off, the total elongation was something. This was 4.5 mm. So whatever they have given, we have related it to the curve. Fine. Let the gauge length be 250 mm. So what they are saying, there is a 250 mm to 25 centimeter long, about this much, 25 centimeter long rod, mild steel specimen was there, and then it extended by about 4.5 mm. So at breakage, so 4.5 we can actually visually see that it extended by 4.5, and it had a diameter of 25 mm at the gauge section. So what does the gauge section mean? We will generally have our specimen like that because we want the failure to happen in this zone, not at the grips. So this will be little bit reduced. So this is what the gauge section is. This is my gauge length. I hope that is clear. So what is the Young's modulus of the materials, what is asked? So we know that the proportionality limit holds till 150 kilonewton, but we have not been given what is the displacement at that. So before that, mild steel follows a linear path, which means we can consider this point. So the load at 40 kilonewton corresponds to a displacement of 0.1 mm. So from here, we can actually calculate from load of 40 kilonewton and displacement of 0.1 mm. We know that stress is nothing but load by area. I think area diameter is 25. So it is 25 squared pi by 4. So my stress comes out to be 40 E3 by 25 squared pi by 4. 81.487 MPa is my stress. My strain is 0.1 mm by gauge length is 250 mm. 0.1 by 250 into 10 power 6 is 400 microstrain. So therefore, Young's modulus of the material is the ratio of these two, which is 8140 E3 by divided by 0.1 by 250, which is 203 GPa. 203.72 GPa. So this is my Young's modulus for this material in the linear elastic zone. That qualifier is also needed. Okay, so this we have got. I'll just copy this, put it here. The yield strength is what? We know yield stress, the load at yield is 261. I'm sorry. The load at yield is 175. So the yield strength strength is load at yield by the area, which is 175, I think it was, by 25 squared pi by 4, which comes out to be 356 MPa. Very well. So this we have got. So this is my yield strength. All right. What else is asked? The tensile strength. Tensile strength meaning up to which it could actually bear it. What was the ultimate load it could bear before it broke off? It was 261 kilonewton. So it is just an extension of this. So I'll just write tensile strength, load at, or peak load, I should say, which was 261. But mind you, we are still taking the original area only. We are not reducing it. That is why this is called a engineering stress strain relation, so to speak. So this will be 261 by 25 squared by. So this comes to 531.7 MPa. I encourage the viewers to check the calculations parallelly. In any case, this is my tensile strength. So far, so good. The percentage elongation of the rod at the end of the test. At the end of the test, what happened? It just broke off. So the percentage elongation was, what was the total elongation of the bar? It was 4.5 mm in a gauge length of 250 mm. This expressed as percentage is around 1.8%, which is quite huge. What is the percentage reduction in the area if the diameter at the neck? So what is the neck? We had the specimen like that. So this was kind of the specimen, let us say. So when it actually failed, here there would have been necking, smaller diameter, and then it would have broken off. So that neck diameter after it failed, it is measured to be 24.94. So therefore percentage reduction in area is nothing but 25 was the original area, 25 was the original diameter, 24.94 square pi by 4 divided by this quantity again. So I will leave it as an exercise for or maybe I'll just do it. Minus 24.94 squared pi by 4 into 100 comes to around 0.48. So this is 0.48%. So this is all fine, but what have we learned from this? So basically, we took a specimen, a mild steel specimen, a dog bone, so to speak, which is complying with this American standard of testing materials. We loaded it. We calculated the different. We actually noted down the loads at different time intervals, and we also noted the displacement. All this comes from a tensile testing machine, and we have to process that data in order to get our Young's modulus, yield strength for this thing, and so on. Once we get these values, we will have to design some component based on this. So anyway, so I have run out of questions, and also nearly we are closing. We are nearing the closing time. So, are there any questions about what we discussed today? Is everything clear? Okay. Anything you people want me to explain from the assignment? Is everything clear there? In case you are attempting them. Okay. So I take it is clear. Well, I hope I've done some justice to explaining the contents of week 5 today. So okay. So other than this, I have nothing more to add. So if there are no further questions, we can wrap up and call it a day. I thank you for attending.